got that. Then said, hold on now, if the bases are the same, and they are base 2, then these two parts, the exponents must be the same. So they quickly did this, divided by x, and that was the answer. So the log of 32 base 64 with some thought behind it is 5/6. Jonathan says, hold on, Professor. When I started scoring his paper, you asked for log of base 64 32. He quickly used the change of base formula. And he changed it to a base 2. So he quickly, I think, Jonathan, help me out. I wrote this as what? Log base 2 of 32 over log base 2 of 64. And this is a 5, this is a 6, and that made it right quickly into the answer. And I'm trying to think, there's another student who showed me something unique. Darn it, I wish I could think of it now. And I kept looking at it, I said, how did that student get that answer? It wasn't the approach I was using on my key. And I kept looking, and finally I thought, wow, the way this particular student was thinking, it did work out. A little bit of a different approach than I had in mind, but it worked out. We get the answer. Okay, guys? Now, what do I do? Well, I've got to. I'll slow you down a little bit. I've got to start recapping this trig. You have a quiz concerning trig on Wednesday. I've got to slow down a little bit and recap trig, and Philip at the same time introduce some new trig parts to us as we move along. Okay? Let's do this. And I'll let you know exactly what that quiz, one question on Wednesday will cover. You guys, I'm a good marker here. Let's do a recap. And I was thinking about, let's see what I did here. This. Here we go. And I'll jump into some problems here. Guys, a little recap here on the trig. If I have this, f of x is equal to sine x. Put a comma. Let's quickly just do one cycle of a graph. What does sine look like as a graph? And I think we check what we've done so far, and I'll do it quickly here. Please tell me it looks something like that. For one cycle. And then we had it labeled. On that one cycle, guys, if you look back in your notes here, we said the domain was, I think, all real numbers. You have one cycle up here for the parent graph, but it continues forever. The range, anyone recall what the range was? From here to here. -1 up to a +1. Gotta know all this. So the domain range, there was an amplitude just in case you ever run into it. It was identified as 1, the highest point from the axis. Now the important thing, Jonathan, I heard you mention this in the 2 o'clock session. The period. At what point might I pick up and do another cycle if I wish? Who recalls? 2 pi. And that's the period number for, and accepted as the period for sine. Let's go play a part. Let's call this letter B. Let's look at next cosine. Look at a few of these with us, just a little recap. You guys call this f of x is equal to cosine x. And just a visual here of what this might look like as a graph. Please guys remind me, I'll mark this. 1 and -1. Did it do something like this? For one cycle. Is this true? You guys recall the cosine graph, the shape? Does anyone recall, without me marking here, what was the domain understood to be for the cosine graph, cosine function? All real numbers. Those cycles repeat forever. The range, though, even on this one cycle, is meant to be what to what for the range? -1 up to 1. Amplitude, if it ever comes out, is also 1 for the cosine. Period, the period number, the number at which you can start repeating these cycles, does anyone recall that for cosine? 2 pi. Now I'd like to squeeze in, let me do it over here, this one. We call it f of x is equal to tangent x. This trig can get busy on us. And guys, I think, if I recall, I graphed mine, and we'll label this one like this, and there's an asymptote at -pi/2, an asymptote at pi/2, and please remind me, did the graph look something like this? For one cycle. And I think I did catch it between -pi/2 and +pi/2, I think, I hope. The period, let's get the domain out of the way first. Now this one, I need some help. And some of my students, when I first introduced this, came up with like little formulas. And would you guys like to have all this on a handout? Would it help to have all this information on a handout? Just look at the handout and you see the period and so forth and so on. You guys want to use a blue marker here. Can anyone tell me what the first domain is? When I know there's some vertical asymptotes, x cannot be that. But I want to know what the domain is for the entire function, not just this one cycle. And I think someone in class, a couple people, came up with a formula, which I liked. Does anyone recall what it was? I'll write this much for you, x cannot be. And then they had a formula that would give me the locations of those asymptotes. Does anyone have in mind what it was?
Pi n, isn't it?
No, I know which one you're thinking of. It's not pi n here.
D over pi.
Here we go.
D over pi.
Okay, period over pi. Tell me more in terms of just a general formula. Let's leave the p out.
2 pi n plus pi over 2
Whoa. 2 pi n.
plus pi over 2.
All right.
That's 2
Here we go.
over
Let me do it like this. I think what, in essence, you're telling me,
yeah.
2 pi plus 1, what? Pi over 2?
Yeah.
I'm gonna check it. Is that gonna give me the locations of those asymptotes? I'm going to write like this. And guys, what I would do, and what I did do when I was a student, I sort of looked at everything I'm giving you today, and I just use the word memorize, but I knew it.
Is there any other formula?
There are.
But
Yes.
you can't do pi
Well, let's
over
check
2
this one first.
plus
Check this one first. Yeah, exactly.
Pi n?
Other versions. Let's check this one. If I replace n by, we're replacing by integers. If I replace n by 0, guys, would this give me just 1 inside here? And 1 times pi over 2 says there should be an asymptote of pi over 2, and there it is. If I replace n by, let's say, -1, that's an integer. If this formula is correct, replacing n by -1, this becomes -2 plus 1, what is that? -1? So I got a negative pi over 2. Was there an asymptote sure enough at negative pi over 2? So I think if I replace, Nima, if I replace n by 1, I think this inside here becomes 3. 3 pi over 2. Would you expect another asymptote, if I should extend my graph, to show up at 3 pi over 2? Would there be another asymptote at 3 pi over 2 if I should extend my graph?
Yeah.
This formula will work. Jonathan,
I won't use
I
that.
know how your mind works, which is beautiful.
It's no good.
Tell me, no. Tell me what you think. Now, this is what I'm going to express my domain as.
It just seems to make more sense to say x doesn't equal pi pi over 2 plus pi n.
Hang on.
Like, why would you do that?
Pi over 2 plus what now?
Pi n.
Here we go.
Because the period's
Hang on.
pi.
And element of the integers. You test your red formula. Replace n by 0. You get pi over 2, and yes, pi over 2 is one of those you can't use. Put a 1 in here, and then you're going to get what? Pi? Combine these two with the common denominator of 2, I think you get what? 3 pi over 2? And I think we just mentioned 3 pi over 2 is another location of an asymptote. If I put a negative 1 in here, for n, you get negative pi. You put negative pi and pi over 2 together, common denominator. Guys, I think you get this one. You do the math. It will work. Of course it will. And I will definitely accept it. Wow. Now, Jonathan, being clever is like you are. I love that. Look back at the blue one that I think Farbod was telling me. If I should do this to the blue one, I like the one I blocked off there. But just look at this. If I should go back to the blue one he gave me and distribute, use the distribute property, pi over 2. Pi over 2 times this, the 2's cancel. Leaves me pi n. Plus pi over 2 times 1, like a distribute property, distributing pi over 2, gives me pi over 2. We're right back to what you said.
The 2n plus 1 thing confused me.
Yeah. Well, you reach your calc course and they say 2n plus 1, you gotta know what that represents. By the way, guys, 2n plus 1, does that, no matter what you replace n by, it's gonna be an integer. Will that always give you an odd answer, odd number for an answer? If 2n plus 1, will that generate just odd numbers? Yeah. And are the asymptotes short enough? I got just a few here. I got negative 1 and 1, those definitely are odd. And then I heard 3, pi over 2 would work. Next, I would think, well, 5 pi over 2 would be another location of an asymptote. 7 pi over 2. So this right here is in mathematics, comes up quite often, this will give you odd numbers. What do you think will give you even? 2n. If you need it. Okay? A little recap. Johnson, I like that though. The red one, go for it. Absolutely, that's true. Okay, the guy says the domain, the strange part of that. Now the range, there's nothing wrong with the range here. It's easy. Negative infinity through infinity. No amplitude. Now the period. Who remembers the period number that would make these values on a tan graph of function repeat? Pi. Now guys, I have the 3 principal trig functions. A little information, a little recap. How many trig functions are there again? 6. Let me do one more. Let's do one more. Letter D. Let me do it if I can. Let me do, let's consider cosecant. Which you know is 1 over sine. You wish to think of it like that. Mark a few things here. 0, pi over 2, pi, 3 pi over 2, 2 pi. Let's go through one complete revolution here. Guys, does anyone recall what, and we talked about this in class, I think what I did, I went back to the sine graph, I think. And since cosecant is 1 over sine, we took the reciprocal of this and got another graph called cosecant. So if you guys remember in class when I did this, I went back to this, used it, took the reciprocal, and that's what cosecant is, it's the reciprocal of sine. So I went back to the sine graph, did like a reciprocal, and got another graph. Does anyone recall what the graph for cosecant, which came from this one and a reciprocal, looked like? Okay, there you go. So there's an asymptote right here. Oh yeah, accept that. Where's another asymptote? Pi. There you go. Gotta know this. At pi over over 2, and I'll go ahead and mark it to give you a hint. Where's my graph supposed to be located at pi over 2? 1, thank you. And we have a little branch looking crazy that did that. When I reached 3 pi over 2, I think we discovered it's -1, and we had another piece symmetric to that first piece that looked like that. There's one cycle of the cosecant graph. Yes? Now let me list the domain, the range, and so forth and so on, and we'll leave this now. Domain, guys, on this one, since I have asymptotes, let's write this as x cannot be. Now, this time, Nalvia says, Professor, it's 0, pi, 2 pi. I might expect the next one to be at 3 pi, asymptote, 4 pi, 5 pi. Is there a good way to write that out for anyone who may look at it to see the location of an asymptote? I need a formula. Is this n pi? Where n is any integer. Replace n by any integer, you're guaranteed you're going to have an asymptote on this graph. And x cannot be that value. Range, well, the range is not 2 after you look at the graph, it's the up and down. The lower part is -infinity up to what? -1 inclusive, and the upper part 1 through infinity. No amplitude to worry about here. Period. Do you want to recall the period number that might make these little pieces repeat if I wish?
2 pi.
2 pi. And that's just a little recap. Does that help? Since I haven't seen you for a while, just a little recap. Aiden, I haven't touched inverses tonight. These are not inverses. These are just your regular trig functions. Here.
Is there a name for the space between the two sections of this graph? If it's not amplitude?
Oh, wait, are you saying from here to here?
From
The cycle?
yeah,
I call
from
it
one
a cycle.
from 1 to -1 on the y-axis.
Oh, up here. Oh, from here to here?
Yeah.
No.
Okay.
Okay, guys, so make sure you understand the domain, the range, the period of these graphs. By the way, I'm not doing secant, it's in your book, in your textbook. What other one am I leaving out? Cotangent. They're all in your textbook, and I think I have all these on a handout also for you later on. Did this help? Bring back some memories? Of course it will. Now, what's so bad about taking this so fast in a fast course like a 6-week course? By the time you get comfortable with this, the next day almost, they're asking you to do an inverse on them. Just, Professor, finally I see the little wave. I finally see where an asymptote might be. Now all of a sudden, the next day, now they want you to do an inverse on it. That's the problem. And that's an issue we got to resolve. Okay, hopefully tonight. Okay, guys, any concerns here? Now, your quiz problem. On Wednesday, your last quiz. I hope to get a 10 out of 10 on this. I brought this in for an example. Oh boy, here we go. With all this said, Aiden? Yeah. I'm gonna do this, part 2, it's all recapping. I'd like to sketch one complete cycle of this function that involves trig. I need some markers here. Now you're going to walk in Wednesday. You're going to say, what on earth? F of x is equal to, and we're going to break this down. Here it is. -5 sine 2x subtract 5 or 8 subtract 3. That's it for a quiz. Just it. One like this. If I were a beginning trig student, But maybe a student that has a little experience with trig, that would be scary. Caroline, I'm gonna leave it up to you guys. If you feel more comfortable doing this through transformations, go for it. Let me count the number of transformations, if you wanna do it. You gotta do the sine parent graph, that's this graph back here, you gotta do that first. And then the transformations, from left to right, the transformations are reflection through the what, x-axis, a vertical stretch by 5, oh, this can be fun. Inside here, there's something first wrong inside the parenthesis to get the next transformation. What should I do inside the parenthesis? What would you suggest? Right here, something wrong with the way it's written. Factor out the 2. You want that x all by itself. So I factor out 2, we're going to end up with x subtract of all things, pi over 16. That x should be all by itself, and I made the x all by itself by factoring out 2. It is pi over 16, isn't it? To take you back to pi over 8. Okay, now, recap. Reflection through the x-axis. A vertical stretch by 5. Uh-oh, a horizontal something by a factor of what? 1/2. Remember that 1 over c. A horizontal shift to the right, pi over what? 16. And finally, a vertical shift down what? 3. Aiden, I realize this is a quiz, and I usually give you maybe 30 minutes to do a quiz. If you had this and you want to go through transformations, you may be here an hour. Because I have some questions to ask after you get it graphed. But just to get it graphed, if you want to do the transformations, and I'm going to leave it up to you. You can do it through transformations. If you're patient, take that parent graph over there and start these transformations. I think, though, I showed you a quicker way to go directly to the graph and not have to show all those transformations. I think I call it bounding. So let's go to the argument. And we'll use this word. Let's bound it. Now, I'm doing a sine graph. What was sine bounded by from here, from this initial to the end? I didn't label for you, but it went from what, 0 out to, I think, 2 pi. The parent graph did. This one, I want the same thing. I want this to be bounded between, written like this. Now, written in my factored form. I want it to be bounded between 0 and 2 pi, just like sine was. So you have to know those are parent graphs, so you can see how to bound these things. Now I got to solve for x. Well, let's divide everything by 2. This is algebra now. And division by 2 will give you, make no mistake, that add pi over 16 to all 3 parts, no problem. Make an x all by itself. Now the problem might be here. We're adding pi over 16. I got a pi already. So guys, what is pi plus pi over 16? Put together with a common denominator of 16. Is it 17 pi over 16? Help me out. Is it? We're going to take this right here and add pi over 16 with a common denominator of 16. Could I make it look like this? And get 17 pi over 16. Yes or no? Okay. So now I know the initial, the ending. Just like over here, the initial was 0 on the parent graph, and the ending was 2 pi. This one has an initial and also an ending. Whew. Now what I showed you last week, and I know a lot was going on last week with logarithms. It was a fast-paced course. So I don't know how much your mind was zoomed in on this. Now yeah, I think besides 0 and 2 pi, I think in between I had a pi over 2, a pi, and 3 pi over 2. I had 3 more intervening points. I need 3 more here. So my initial is this. My ending is this. Now that's enough for me to find the period of the graph. Just take the ending, which is a little strange number here, subtract the beginning. And whatever that ending subtract the beginning is, guys, just like a 16 pi over 16, oh, 16 there. And I think I'm going to end up with pi, see if I'm correct. Is that true? So the period is pi. I think the period on the parent graph is 2 pi. This one has a period of pi. Now, I usually ask you to divide by what to get the spacing? 4. Why 4? 4 quadrants. If I divide by 4, that means the period is being divided by 4, guys. The period is pi divided by 4. This gives me my spacing number. So I can space by it. 5 and 4. Woo! Yes?
For the quizzes, all right, if we call the spacing 4 pi over 16?
Absolutely. Absolutely. 4 pi over 16. Okay? Now let's go to the grid. Start putting this together and see if I can get it to work out for me. Find another space here. There we go. Guys, only one cycle. That's all I need. For Wednesday's quiz. Okay, the beginning is pi over 16. It ends at 17 pi over 16. That's like 0 to pi. Just like the parent. Now, how about those 3 intervening points, like on the parent graph is what? Pi over 2, pi, 3, pi over 2. We found the number to space by. In fact, Jonathan, this pi over 4 with my 16s staring at me, would be nice to write this as what was it, 4 pi over 16? That's still pi over 4. So we're spaced by 4 pi over 16. So here, add 4 pi over 16, you're up to 5 pi over 16. Add another 4 pi over 16, you're up to 9 pi over 16. Add another, you're up to 13 pi over 16. And if you add one more, that takes you out to 17 pi over 16. Now they're evenly spaced. All this making sense? Looks so much like the parent graph, except you got strange numbers here on this one. Okay? Guys, please, before I start here, 0, pi over 2, pi, 3 pi over 2, 2 pi. Just like a parent graph. Except this one has different values to work with. Now, Miriam, I've got it marked. So this, I usually do this so students will not look at it again until we start checking something. This, do not look at again right now. That's gone. We've done that. All I'm interested in now to get the graph is it should be shifted down 3. Vertically, oops, or it's supposed to be upside down. And a vertical stretch by 5. And that would give me the graph. You guys are good. I'm going to do that vertical shift down 3 first. Here goes. Got numbers in just in case I need them. Guys, my axis is now down here. Let me put that in red. It is here. Make sure you see it. I'm down at -3. That's my axis. That's my vertical shift down. The graph, it's a sine graph. I don't know what the parent graph looks like. It starts at 0 and then what goes up. This one should start at 0 and do what? Go down. Go down how much? Well, it all depends on this stretch. So it says, please go down to your axis and show right now maybe a stretch of 5 up, a stretch of 5 down, and they'll give you a start. Guys, I'm at -3 now. If I stretch it 5 more, where eventually will I land? I'm at -3 right now. Where might I land down here eventually? If I stretch it 5 more. 8. -8? Okay, 4, 5, 7, 8. Aiden, since you're helping me out, I'm back here. Now, where will I land if I stretch it also 5 up?
2.
He tells me 2. And all he's doing is taking -3 and the -5, putting them together, you get -8. And then 5 subtract 3 gives you what? A 2 there? So he's doing a little arithmetic there. So 5 up, 5 down, guys, that's your vertical stretch. Takes you down to a -8, takes you up to a 2. Everything's marked for me, I think. Here we go. Sine graph. It should start at 0. Miriam, does that mean at pi over 16? I think that's my first point. Was my first point pi over 16? What? Should it be on the axis, in other words? Is that like 0? For us. The next one, the parent sine graph went up to 1. This one is going to do what? Go down. It's being reflected through the x-axis. And I would think it's going to go down at 5 pi over 16, probably down to a -8. Would you guys agree? Is that true? The next point, I would think, might take me to where at 9 pi over 16. I think it's going to go back to the axis. Let's see if it does. Mark this. Let's see if this is a little better, a little bit better. Here, what's going to happen at 13 pi over 16 with that sine graph, a visual of it upside down? Up 2. And finally back to the what? The axis. Connected? There's a rough sketch of one cycle of the graph. And before I start asking for domain, range, period, amplitude, if there is one, and something else on the side here, does anyone have a question about just to get to that point? Can we have the quiz on Wednesday at least get to that point? That's going to take a little thought. Rebecca.
What about the 2 that you took out?
How about the what now?
The 2?
I'll be, hang on.
Oh, no, never mind.
I've already divided by 2.
Yeah, never
We got rid of it. We got rid of it. Guys, anything else to ask about?
I actually have another question about the 2.
Go for it.
Is it like, when we think of the 2 in the argument, is it kind of like we're compressing it like a accordion?
By a factor of 1/2.
Okay.
I think on the handout I gave you guys way back was 1 over C. They call it C. And C in this case is what? 2, so it's 1/2. It is compressing, squeezing in by 1/2. Okay. Now, my little method is not going to show all that. If you did through transformations, you probably would see it better. Mine, I just want you to make sure you see in the calculus, they just want to see a cycle. They want you to see what one cycle of this graph may look like. Guys, it's amazing, for even as an instructor with all the math I've had, this represents this. That's his picture over there. That's his name. There's his picture over there. Okay. Any questions to get to this point? Okay, guys? Now, let's identify it like I was identifying over here. The domain. I think we lucked out here. Any asymptotes to worry about? No. The domain will be -infinity through positive infinity. It goes up forever. Range, I don't think the range is going to be too bad. The up and down, if my graph is correct, I think it's from -8 for the low up to what? 2 for the high. The up and down, the range. Period. I would suggest you take the ending, subtract the beginning, which I think I've already done. I think it's pi. I think if you check out the graph here, it is, again, going to be pi. The ending, subtract the beginning. Okay, domain, range, period. Amplitude, if there is one, Jonathan, it should match up with this number. if there is one. Can I sure enough say the amplitude, the distance from the axis is 5 for the max, and also 5 for the min? Do we actually go 5 from here up and 5 down, give me a -8, so 5 is my amplitude. There's always that coefficient stuck out front. Wow, wow, wow. Now, it's gonna take you a good 30 minutes. Oscar, it may take us a little bit more than 30 minutes. You say, Professor, it's just one problem? One problem? Caroline, what else am I gonna do before I leave this? There's the graph. Now, this is where you get to feel good before you leave. Feel good about your answer, your graph. I will choose one of these 5 critical numbers and ask you to do a check, algebraically. I'm gonna choose, just at random, I'm gonna choose 5 pi over 16. So I'm gonna go back to my function and find this. Algebraic. Go back to my function, replace x by that, crunch it out. If I do not get, the graph says the answer should be -8. At 5 pi over 16. If I don't get -8 algebraically, I know my graph's wrong. If you guys can check this, if I go back to the original, it's -5 sine, and I'm going to write this as in the factored form. Remind me, guys, what was the raw formula, the original? Well, let's go back to the original. 2x subtract pi over 8?
Yes.
Okay, so it's 2 times x, and I'm looking at 5 pi over 16. Subtract pi over 8. What a mess. Subtract 3. Here we go. We're hoping that it will agree with the graph. Here we go, guys. -5 sine. Now here's where you might make a mistake. It's the algebra. I know some of my exams and quizzes, it's algebra, it's not pre-calculus. Students are messing up on 1 + 1. Okay, guys, on the first term, just do a little canceling, and makes that 5 pi over 8. So it's 5 pi over 8, subtract pi over 8 inside, which is what, 4 pi over 8. Better expressed in reduced form as pi over 2. And of course, I've still got that. Here we go. This now says -5. Now I need from the unit circle, who recalls what the sign was at pi over 2? 1. Sine of pi over 3, sine of 90 is 1. 1. But subtract 3 on the end. So we end up with -5, subtract the 3, and we end up algebraically with -8. Does that agree with the graph? And that will make you feel better, I think, when you walk out and say, I think I got the graph correct. Now, how many other points though are on my 1 cycle? There's 4 more. I should check all of them, but you don't have time to check all of them. So I ask you to check at least 1. Guys, this help? Do a little recap here. Okay, I don't want anyone to walk out and say, oh my goodness, this pace is so fast, and it is fast, Professor. So far so good? Okay, now, I will tell you also, I'm going to stick with sine and cosine for your quiz. So I'm not going to ask you to do a tan or a cosecant graph, not on the quiz. That'll be on the exam Friday, but no, Wednesday, it'll either be a sine graph like I did, or a cosine to do one of these crazy drawn out problems here. Okay, guys? Yeah, races. Woo! Now, where does this take me? Take me back into chapter 6. Takes me right back to where I should be, and I'm gonna move along here and show you why I checked that view in chapter 6. Beautiful. Here we go. Oh, I'm so glad I did this. I am so glad. I'm gonna leave this for a reason. Now, part 2. quite much in part 2 tonight, guys, on the chapter 6. For a start, let's do a little recap of something we did last week, and that was this. Inverse function. Notation. Please tell me, did I ask you guys to find an inverse for me on that last test? Did I? I asked you to find the inverse, didn't I? I think I gave you a log, and I asked you to find the inverse of it. It came out to be an E raised to something. I think it's E raised to something. I think I gave you an LN, I think. You had to find the domain, the range, and so forth. Same thing on these. Except, darn it, we looked at this earlier. If I saw this inverse function expressed like this, basic sign, but with a superscript of a -1. This means, when I see it, sine of y is equal to x. That's its translation. Dropping the log in the translation for the log, now you just drop the inverse. Means sine y is equal to x. Now, another issue. Does anyone recall? I'm going to do it right here. What is accepted for the domain, that's the x, for an inverse sine, and I recall I drew the sine graph and then chopped off a part of it to make it 1-to-1. Does anyone remember what the domain was left over for the chopped off part?
-pi/2.
The x, the x. -1-to-1. And does anyone recall what the range was? This is the y. I'll put it right here. What the range was supposed to be. That's my domain there. For the inverse sine, after I chopped off that piece. That's where we sort of stopped, I think, last week. You guys had your mind on logarithms. Tell me again. Nothing. Oh, we did lose it. Oh, that's why I was seeing some issues. It's the inverses then. Professor, it's not this so much. But the inverses were where they chopped off a piece of it to make it 1-to-1 and gave you the domain to be this, and the range came out to be something else. What was it? -pi/2 up to +pi/2. That's the trouble on these inverses. You have to memorize or know domain range, especially that range. That means, guys, there's my meaning here. If I saw this, inverse sine, 1/2. And they ask you what answer. You say, well, Professor, looks like they're looking for something out there when you take a sine of it. Take off y. It's equal to 1/2. That's the translation. Sine of y is equal to, in this case, x is 1/2. Now, does anyone recall in the unit circle where the y coordinate was 1/2? At what spot? What angle? I heard 5 or 6. Now, if another student said, wait, Professor, how about 5 pi over 6? Is that, please tell me, at 5 pi over 6, is it also 1/2 sine, which is a y coordinate? You say, wait now. I thought these functions were supposed to be 1-to-1, but all of a sudden I see on the unit circle, Professor, another possibility of this will also give you a y coordinate of 1/2, or sine. I can't use both. That's why they gave you, or will give you, these restrictions. They weren't only one answer. So you got to choose the one here that fits between -90 and a +90. Guys, 5 over 6 is like 30. Would that fall between -90 and a +90? I think this radical degrees is 150. I don't think 150 will fall between these two, even though it works on the unit circle. So they want just one answer, and that final answer in this case is inverse sine 1/2, I'll just rewrite it, is equal to pi over 6, and that's the answer. That's what's going on. You have to know, memorize these restricted intervals. Now I'm gonna do the sine, cosine, tangent. If you move to a Math 7 class, and Mr. Park, I don't know how much you remember about your Math 7, Math 8. I'm sure they did also inverse secant.
Mm-hmm.
See? Inverse cosecant.
Mm-hmm.
Inverse cotangent. I'm gonna do 3. I'll leave the other 3 up to you. They'll be in your math textbook. I'm going to do inverse sine, which I'm talking about now, inverse cosine, and inverse tangent on these. Guys, let's try one more here, example of what's going on here. Let's separate this, we finish with this. Next problem may look like this. Find the inverse sine. Rebecca, I'm going to put a negative 1/2 this time. And all it comes down to in your mind when you see that says, okay, professor, you're asking me to reflect back to the unit circle and find a spot or spots where the y coordinate is negative 1/2. Can you name one for me?
Negative 5 or 6.
Whoa, she's already got the answer, Donnie. She is quick, she is quick. Tell me though, if you were just looking at the normal unit circle, tell me on the normal unit circle, where is sine equal to a negative 1/2?
7, 5, 6.
Hang on. And I think there's another spot.
5, not 5. But 11, 5 or 6.
11, 5, or 6? I agree with her. You check out the unit circle at 7, 5, or 6, the sine, y coordinate is negative 1/2. 11, 5, or 6, y coordinate is negative 1/2. Oscar, we've satisfied what the red says, that's what the red says to do. We've satisfied it. Darn it, both these work. But to make it 1-to-1, and I mean really, this one's really strange. Your answer's got to fall for inverse sine between these two always. Now we're doing it in degrees. Guys, I think this is 210 degrees. I think this one's 330. There's no way 210 degrees is going to fit between negative 90 and a positive 90. And 330, no way it's going to fit between negative 90 and a positive 90. So, even though these work, Miriam, I can't use them because of this. I wish inverse sine had no restriction, but it does. Then all of a sudden, Rebecca gets creative on us. She's a professor. Maybe I can do this. I mean, she is clever. For an example, I'm doing it in degrees, guys. 330 degrees at 11, 5, or 6. That's what it looks down in quadrant 4. She says you can't use it, professor, based on this. But won't you rename it as that? In degrees, that would be like negative 30. Backwards. They stop the same place. Or better yet, in radians, that's a negative 5 or 6. And she says, professor, mark out those blue and accept this. Negative 30 for your answer. As long as it falls between these two. And it does. Negative 30 falls between negative 5 or 2 and a positive 5 or 2. Farbod, we're not going to do well unless we know these restrictions. And with the limited time we have, I'm going to hold you responsible for only inverse sine, inverse cosine, inverse tan. Mr. Park's already saying, though, after you leave me, that also you need what? Inverse tan, inverse cosecant, inverse secant? You need all those. I'm going to just focus on these 3. Okay, guys, we'll try one more here with the sine. Inverse sine, negative 1. Tell me directly on the unit circle, you know what that unit circle looks like. Tell me where is there a spot on that unit circle where you've seen the y coordinate sine equal to a negative 1?
3 pi over 2.
3 pi over 2, right? 3/2. She's right, Professor. I know my unit circle. You look at 3/2, the y coordinate is -1, and the y is sine. Darn it, it will not fit here. They did this to us just to make it 1-to-1. Only 1-to-1 functions have inverses. That's the trouble here. We've got a restriction. It will not work. Aiden, can you tell the class another way to express 3/2 that might make it fit?
I don't have my glasses.
Oh, you don't have your glasses,
I
you
can't
can't
see
see,
the
okay.
restriction.
Okay, let me show the class where it is. That's 3/2 that he gave you. Nima? Nima, you got glasses?
Yes.
Okay. Nima, tell the class how another way to name 3/2, and now it will fit the restriction.
You can say 2 pi minus,
Oh, no, just give me an answer. I love this kid. His paper, he checks and checks and rechecks and checks and rechecks, and writes me notes, Ramsey, is this correct? Checks and rechecks. I love it. So that's a quick way to show. I think I got it. Ray,
It's -5/2.
she said, Professor, just move the opposite direction. You stop the same place. Which means now, name this what? Negative. You went backwards, clockwise they call it. Don't use this, use this. And Ray says -π/2, Professor, thank goodness they put a bracket on this, is included. And there's the answer. Miriam, I wish I had said calculators for the exam on Friday. If I pass out the calculators, they all have inverse keys on them. Miriam, you just press that key and it flashes on the screen. Isn't that nice? Oh boy, I saw a nice article last night before I finished up your papers. Oh, by the way, it took about 6 hours to score the papers. Being very honest, about 6 hours. Got done, it was wiped out. So I was watching something, streaming something on TV. And now they're showing now the AIs being placed into the classrooms. And showing kids, like middle school kids, elementary kids, they all have their laptops. They're in elementary school. They have their laptops. And the teacher has a laptop, and they're asking AI questions. And they just sit there and think, oh, wow. They get to phrase the questions, they try to trick the AI. They try to trick it some way, and I saw a few ways they did trick it, and AI gave them the wrong answer. And the voice came out, oh yes, that's the area of the triangle. It wasn't. It was cute. Now can you imagine doing this when I passed out calculators of some sort on Friday? Wouldn't that be nice? And for us, just press keys, and you get the answer. All these calculators have inverse signs on them. So we're not gonna do it. So guys, -π/2, that's it. Now, Jonathan, this is for you. Part B. I'm closing this down. Because I heard the concern before I came in tonight to class. I heard from my 2 o'clock session. I love my students, no doubt. And I realize the fast pace will just drive you nuts. So Professor, could you please just recap some for us? I'm recapping before I really jump into some work here shortly. Okay, the next one here, let's try f of x is equal to inverse cosine. That was another one where we had to chop off a piece of the graph, in fact, a piece of the cosine graph over there, to make it 1-to-1. That was the issue. Does anyone recall? This means, first, you're taking, that's like a y here. It means cosine of something, y, is x. Does anyone recall what the restrictions on the x and the y were for cosine? Let's get the x out of the way first. Does anyone recall the restriction? -1 up to 1. Nothing else will work. In fact, I think that was also for inverse sine. It's domain, dx. Philip, do you recall what the y, the answer coming out the range? What was it for, inverse cosine?
It was negative pi over 2.
You're getting mixed up.
Was it like negative pi?
I'm getting mixed up.
Oh yeah, was it?
Yep. I'm getting mixed up. What was it? See, that's the problem on this. Yeah.
I have to draw it. I have to draw the parent graph.
Absolutely,
first
that
on
takes-
time. I have no way to memorize it.
No, if that takes a little sketch on the side there, go for it. Does anyone think they know what it was though? Cause I went through all this with you guys. Is the range, was it 0 to pi?
Yeah.
And that's for inverse cosine. Farmon, here's the problem. This one's for inverse cosine. This one's for inverse sine. They differ. So I gotta be very, very, very careful here. Let's try some examples. Inverse cosine. I'm gonna try the 1/2 again. Translated, where on the unit circle have you seen the x-coordinate, cosine, equal to a 1/2 to begin with? The x-coordinate, which is cosine. You check out the unit circle. I heard pi over 3, let's name all of them we can see. Pi over 3 is one of them. And I think there's another one. Oh, what is it? I think it's 5 pi over 3. Miriam, I can't use both. It's supposed to be 1 to 1. That's why they do this. You have to accept the answer that falls between 0 and 180. I think this guy's is like 300. 200 degrees, so that's definitely not gonna work. So inverse cosine 1/2 is pi over 3. Number 2, try another one. Inverse cosine, radical 2, negative. Negative, radical 2 over 2. First, let's pick up those that are directly on the unit circle first.
3 pi over
I heard 3 pi over 4. And I think there's another one, 5 pi over 4. Caroline, is that you? Who was it? Tell me those answers. Miriam. She's correct. Would it help if I, on this quiz only, Wednesday, make a copy of the unit circle? You have a copy, but I want my own copy. And let you use it? Would that be helpful if I actually gave the unit circle to you for Wednesday? I'll do that. Philip, don't you mess up on this quiz. Because you're gonna have that unit circle, you're gonna have all this beautiful explanation, and you're gonna just search that unit circle and try to get the answer. Miriam's already given it to me here. Miriam, if this number right here, 3 pi over 4, if you like degrees, that's 135. If that fits here, we're done. Does 135 fall between 0 and 180?
Yes.
She's finished. That's the answer. No need to even worry about this. You're done. Last one, far above. You did a great job on that test. Here goes. Inverse cosine 2.
Undefined?
Tell me.
Undefined?
Undefined. Now you gotta tell the class why. He said, Professor, there's no answer here. Tell the class why I cannot find an inverse cosine of 2.
It's not in the domain?
Got to fall between -1 and +1. Wow, I'm so glad I did this. Jonathan, you and your classmates who were with me at 2 o'clock, I was not planning to do this. I'm glad you were there to tell me. I think it's helping. Before I move on, because I was gonna move on. Now eventually I will, but this took a chunk of my time here, but I gotta do it. Okay. Let's see. Michael, before I leave this one, let's try this. Or tell me what you think about this one. First, inverse cosine 1/3. Michael, if you have that unit circle, which I'm gonna bring a copy in with, and give you guys a copy during the quiz. And you search that unit circle and find where is the x coordinate cosine equal to a 1/3, Michael said, He shook his head now. It's not there, Professor. It's not on the unit circle. Now, is there an answer on this one? Well, since 1/3 falls here, it's in the domain. 1/3 is caught between -1 and +1. There's an answer. I would have to depend upon a calculator. We do press that inverse cosine key and put it in 1/3. You'll see on the screen the answer. The answer, Aiden, is just not on that unit circle like Michael told me. But there is an answer. Okay, last one, guys. I'm wholly responsible for it. It's this one. Whew. Which means this. Let me write with y. Tan of y is equal to x. Now, can anyone, for your last one, you have to sort of know for me, what was the domain accepted as the x for inverse tan? Who recalls? I think I did inverse tan last week. It's all real numbers. You may replace x by anything you wish, which is unusual, but it is for tan. And the x, that's my domain, of course. Guys, the y coming out, the range, was there a restriction on where the answer coming out should be located? Who recalls? Or maybe I should go ahead and fill this in. It's between -pi/2 and a +pi/2, Jonathan, but this time it's not included because there's some asymptotes on this graph. Much like sine. Sine was -pi/2 to a +pi/2, but it's included there. And with that said, if you know that much, we're good. Let's try a few examples, guys. Here we go. Inverse tan. This one could be a little bit harder to find on the unit circle. Inverse tan 1. Now you know what tan's definition is? Y over x. So this even with the help of the unit circle, you got that y over x and try to find where is it 1? Where is it 1 on this unit circle? Does anyone think they know a spot or spots? Oh, I see a hand one already raised.
45 degrees.
She says, Professor, it's pi/4. But Ray, just out of curiosity, is there another one on the unit circle besides 45 degrees pi/4?
-pi/4?
No, on the just regular unit circle.
Oh,
Michael, what was that?
225.
Come again?
9.
225. Hang on, I think it's the wrong quadrant. Oh, whoa. 225. I put it in radians. pi/4.
Because I think 9.
Whoa, hang on. On that unit circle. pi/4, Ray gave you pi/4. Y over x at pi/4 will give you a 1. I agree with 100%. Michael said, hold on, Professor, also down in quadrant 3, I think it was a 5 pi/4. I think you place the y coordinate over the x coordinate. By the way, those coordinates are both, I think, what? Negative radical 2 over 2?
Yeah.
But one over the other, you get 1 also. He is 100% correct. Those are the only two. Now, Farbod, look at this. If 45 degrees that Ray gave me falls between -pi/2 and a +pi/2, -90, +90, we're done. Does this fall between? Is it within that interval? If so, there's the answer, and we're done. Michael says, this one works, Professor. It does, but it does not fit here.
Isn't that -1? 5/4?
5/4 is down in quadrant 3.
Oh.
Those weekends. Okay. Geez. Okay. Down in quadrant 3, where everything's negative, so it's been a negative over negative, positive. Now, number two, try one more here. Inverse tan, thank you, Ray, for that. Inverse tan. Here we go. Oh boy, hang on, guys. Gotta think of a nice one for you as I stand here. Why not? And without you worrying too much, I will say, even if you did calculate, this number right here is strange, but it is, of course, you can use anything for tan, put anything at all in there. Now, can anyone help me? Michael, if you read that unit circle, this is tougher, and you put y over x, you're supposed to get that strange expression. Is there one, in fact there's two, on there that would give me a negative radical 3 over 3?
Obviously.
Come again.
Oh no, that's not right. It's 11, 5, or 6?
Oh, see how tough this thing is? Rebecca, tell me again.
11, 5, or 6?
Okay, now, hang on, 11, 5, or 6, hang on. Put a little comment there. What was the ordered pair directly on that unit circle at 11, 5, or 6?
Radical 3 over 2, comma, negative 1/2.
Gosh, right there, she's a professor, if you pass out the unit circle to me, that's what it is. Now, they want tangent. Well, I want tangent. So tangent should be y over x. She would be placing this over this. 2's cancel, rationalize. Get that. Now, she told me, what was it, 11, 5, or 6? I'll put it right here for right now, thank you. And Michael, is there another one?
2, 5, and 3.
7, 5,
5, 5.
Oh, all right.
5, 5,
5, 5,
Is it 5, 5, or 6?
Yeah.
Yes? And you check that, make sure you get that strange number, negative radical 3 over 3. I cannot accept both. I gotta just get one answer. Here goes. Jonathan, this is like, if you like degrees, this is 330 degrees, I think. 330. We're supposed to fall between negative 90 and a positive 90. No way is 330 going to fall between those two. So even though this works, that Rebecca gave me, I can't use it. And Michael says we'll try 5, 5, or 6. That's 150 in degrees. 150, does 150 fall between negative 90 and a positive 90?
negative 5, or 6.
Now, Rebecca says I'm gonna get clever. I'm gonna rename, and you told me we should rename and get finally an answer of
Negative 5, or 6.
negative 30 degrees, which would fit between these two. Wow. Now, Rebecca, before I leave this, she said, Professor, if it's not there, and I think there should be an answer, but I just can't find it directly on the unit circle, I gotta be clever here. That 11, 5, or 6 that she gave me earlier, quadrant 4, like 330 degrees, let me help in degrees. She says it won't work, it's not gonna fit the restricted interval, but why not rename it and go backwards, negative 30. It's actually the same, it's going backwards over, maybe the same place. And therefore, call it negative 5 or 6. And therefore now it will fit here. I'm glad I did this. Jonathan, I don't think I would have done this if you guys had not heard your conversation at 2 o'clock. I had something else planned. And I thought, hold on, if my students are now, I gotta do this. Okay, guys, took a good chunk of my time, but we did it. Did this help? Did this help? Please tell me it did. I hope. Okay, guys. I will give you the unit circle on Wednesday. You can check out that unit circle. Mary, before I leave. Before I leave. them before I leave. Why not? Now, why am I doing inverse tan first? Inverse tan of 0. 80, I know you can't see, but that domain is the only one of the inverses I've discussed. Inverse sine, inverse cosine, inverse tan. The only one that has for the domain, you may put anything you wish in there. That should be an answer. So where on that unit circle have you seen y over x come out to be a 0?
Zero. Just zero.
If it is 0, what ordered pair were you thinking of on? Was it 1, 0?
Yeah.
If you place y over x, you're placing 0 over 1, which is 0. And if it is 0, I hope 0 falls where it should fall, or the range between these two. Does 0 fall between a negative 90 and a positive 90? Definitely. Nima, I think when I pass that unit circle out to you to close down, I think there's another spot on there besides his 0 that would also give you the y over x to be a 0. Where is it? Besides 0.
Negative pi?
Can I get it?
Negative pi?
Pi.
Pi, yes.
I think if you check the unit circle out at what, pi, if you place y over x, and that's 0 also? Why can I not, he gave me 0 for an answer, why can I not use pi, 180? It does not fit here. That's the trouble with this. Geez, Rebecca, tell the class there's one more that I can think of on there, that if you place y over x, you get 0 again. Not pi, we got pi out of the way. There's another one. 2 pi. One complete revolution back to 0. And why can I not name it as 2 pi? 360? There's no way 360 would fall between negative 90 and positive 90. That's what inverses are all about. So please, Wednesday, know these restricted intervals for those inverses. Okay. Mr. Park, you don't remember right offhand the inverse secants restrictions, do you?
I remember.
You do?
Yeah.
I'm not gonna hold my class responsible. Look at this kid. Okay, I'm not gonna hold you responsible. What was the inverse secant?
Wasn't it 0 to pi? Am I wrong?
Oh, I think you're right. Okay, now I'm gonna leave those last 3
Right.
for you when you finally enter calculus. And I'll find out who the instructor is. And I'll find out when the first exam is. And I'll sneak in and look at you as you're stressed out taking that first calc test. I'll say, Professor Angel, what are you doing here? I'm just watching. I would check on you. See how you're doing. Okay, guys, I took a chunk of time here. I think this helps. I think this helps. We got a few minutes here before break. It took me all this time to do it, but I think it helped the way we did. Jonathan, you feel a little better about this?
I feel like I understand the 2 theta one a little better,
Okay.
because then it turns into the whole period is pi, so then it goes around, it can go around twice, or even 2 pi.
Miriam just told us that.
Isn't that where you, I didn't, I was like.
Yeah,
but
absolutely.
I thought about it.
You actually graph it, yeah. It squeezes it in. Absolutely. But I can imagine you guys doing all this. This is 16 weeks of working 6. I just got another one of my colleagues, his class is sort of complaining in math 8. He's saying, I'm not complaining now. Because it's so fast. But we do it. But I'm gonna make it very, very doable. Okay, guys, I can't waste any time tonight. Let's call this part 3, I think. Let me just get a start, and we'll take a break here. Part 3. Mr. Park,
Mm-hmm.
I have your name written here for a reason. This way we're gonna close down. I'm gonna have you help me. I don't put you on the spot. Think of a good way to do this. Okay, close it down. And we'll take a break. You guys, I have all this on the handout for you later on. And I have this. You guys, I'd like to sketch, if I could, this on this particular interval. Just on that little piece there, like just a graph. What the sine graph looks like just there. Guys, 0, sine of 0, 0, we know that. Pi over 2, sine of 90 is 1, it's here. Sine of negative pi over 2, not much thought here, negative 1, do this, get in there. That's it, negative 1. And guys, did the graph look something like this? That's a little slither, a little piece of the complete sine graph. That's what I was doing last week, I think, to introduce all these inverses. Mr. Park, come on up, my assistant. Come on.